Hi, my name is Jarrett Latty, and this is my digital sampling lab for AE2610. So the motivation for this lab is to study time-varying signals. Now, time-varying signals are going to be essential to most experiments we might be doing going forward. So we use a DAC to analyze these signals with a time dimension, and this will allow for more accurate experimentation in the future. So the objectives are to introduce the measurement and analysis of time-varying signals, and then practice using digital data acquisition system, or a DAC. So a little bit of background on digital data acquisition systems, which is what is being used to study the waveforms in this lab. They use an internal clock where it takes a sample after some fixed interval t. The sampling rate is equal to 1 over t, and the record length is going to be the time that the DAC is sampling. So the DAC software is also capable of using a Fourier transform to separate the individual waveforms that make up the recorded waveforms that allow for further analysis. The approach taken to the lab is as follows. For equipment, we used a LabJack T4 DAC and its associated connectors, a 3.5mm breakout adapter, and a microphone breakout adapter. The first experiment was using the 3.5mm breakout adapter to connect the DAC straight to the computer. We used the power spectrum to identify 10 mystery given waveforms, and then we further observed power spectral aliasing and the effective sampling rate on the resolution using those 10 waveforms. Before moving on to a experiment of our own design, we had to validate the microphone. So set up a tone generator and record power spectra using the 3.5mm direct connection and the microphone, and then compare the relative response of the recording components. So power from the microphone and the power from the direct connection using 3.5mm jack at all set tone frequencies. So here are the track identification results. I won't go through all of them. The important ones to note are your triangle, square, and ramp waves, which we see all have multiple component frequencies. So you see they all have a 1,000 hertz primary frequency with some higher frequencies that aid to adjust the form of the wave. We also had two that had noise mixed in, so not quite crisp, clean waves like we saw in the regular single sines. We also were able to see the sum of three sine waves where each sine could very easily be picked out of the power spectra. The multiplication of sines you see as kind of a middling point at about 1,000 hertz with plus or minus 100 hertz on either side. And frequency modulation, you would see the frequency range from about 40 hertz to about 1,000 hertz. So the personal experiment that I conducted was to identify the scientific background behind the music that a guitar makes. So the experimental question was to scientifically determine how guitars produce different sounds. So the frequencies of pure strings, the effects that the frets have on the frequency of strings, and if plucking two strings produces the sum of two frequencies. So in my success criteria for this test were if the experiment provided accurate starting frequencies for each string on the guitar, and then if the experiment provided a pattern for what each change in the guitar, such as using frets or combining the notes, does to the frequency. For the guitar experiment procedure, you would set up the guitar with a standard tune and an amplifier. First, then connect the microphone to the DAC and place directly next to the amplifier to reduce noise. Some validation was done using a tone generator to make sure that the microphone and DAC were connected and running properly. Set the sampling rate to 2,000 samples a second and a sampling period of 1 second. Play and record a power spectra for each string as you start from E low to E high. Then using the E low, which is the thickest string, record a power spectra sample with each fret held down, 1 through 12, and then record the power spectra when two notes are plucked at the same time. And then going into data reduction, using a MATLAB script, filter out any extremely low amplitude noise. That was any amplitude of 0.005 VRMS or lower. I went ahead and filtered out because it had no significant bearing and it would make the graphs look cleaner. And then plot the reduced power spectra data on a bar chart. So here are the reduced power spectra produced from the pure note test. And we can see that E low is our lowest frequency note at around 86 hertz, with E high being our highest frequency at about 320 hertz. And that correlates very strongly to the thickness of the string. So, a secondary effect of this test is we've learned that the thicker the string, the lower the frequency when it's plucked. And we were also able to identify very solid starting frequencies for each of the individual notes. Here are the power spectra for the fret test. The no fret test produced a very similar chart to the pure note that we saw earlier with just some slight change in the background noise. And the general trend is that as frets are engaged, the frequency tends to go higher and higher. The resolution on my specific set of testing variables in the frequencies I was sampling with the power spectra wasn't super high, So the only time you would see a significant change was we saw a change at the 4th fret, the 7th, the 10th, and the 12th fret. And we'll go into this further when we talk about error. Here are the combination notes, getting by plucking two pure notes at the same time, and you can see two very clear power spectra corresponding to the same frequencies that we recorded as those pure notes showing up on the slides. Some brief results put into tables. We have the principal frequencies of all of our major notes on the guitar in pure notes, the results from our fret number and frequency changes, which will be used later on in the discussion, and the relative response from the validation data. And you can see that approximately the data follows that as the frequency increases, the relative response of the system also increases. So a brief discussion of the data. We, like mentioned before, the notes correspond to the thickness of the strings, with thicker strings producing lower frequencies. And some further research could be put in on if different guitars produce different principal frequencies despite having the same tune, or if some of the background changes might change with the guitar-specific sound. Now, for the fret test, a pattern was discovered. So across all 12 frets, the frequency is doubled. Using that information, I formed a hypothesis that the fret would take on some form of an exponential increase of 2. So through some trial and error, I found that the frequency of a note was found to be 2 raised to the x times 12 times whatever note you're plucking, where x is the fret engaged. And the combination test showed that the graphs showed two peaks corresponding to the measured pure notes from before, so we can conclude that combination notes, where you're holding two strings, are just a sum of the two individual frequencies that are being introduced by plucking the two strands. Using all of this information, any frequency that is wanting to be produced by the guitar can be used using the starting frequencies of the pure notes recorded, the pattern for the fret engagement we found, and then if we want to add some different levels to it or add a second note into the combination, we can do that by simply plucking another strand at the same time. Some brief sources of error. There was likely some ambient background noise in the room that made its way into our power spectra. Each time we plucked a note to record, sometimes the pluck wouldn't be exactly identical, which may change some of the way the note is recorded. So there was likely some random error introduced by the amp as well, and obviously some error in how the microphone is reading. So a more accurate test would involve directly feeding the guitar into the DAC through some sort of breakout, and the resolution of the power spectra could have been improved by resetting the bounds closer to the range of expected frequencies, because we now know that guitar frequencies will range from approximately 75 hertz with an upper bound of about 450 hertz.